Okay, so we're going to pick up where we left off yesterday. Welcome to Lecture 2 of an Introduction to Standpoint Logic. Yesterday we had ended by discussing nested sequence, what these structures are that are going to be used in our proof system. And now we are going to go through and look at the various rules in this proof system and understand how proofs are built using these rules. So I'm going to go through the rules one by one and explain what applications of the rules look like so you can see how they're used, and also explain throughout the process why these rules are sound, which will give you an idea about how to read them. And then after that, we will look at how to build proofs and also what are called derivations in this system. Okay, so before we talk about those rules one by one, I'll talk a little bit about soundness since we're going to be showing these rules sound. We define a rule to be sound in a sequent calculus if and only if, for any instance, or also called an application of the rule, if the premises of the rule are valid, then the conclusion is valid. So a rule is sound when it preserves validity in a top-down application. Okay? And we have a lemma here which rephrases this definition in terms of invalidity. This is something that I talked a little bit about last time. So this is an equivalent characterization of soundness. A rule is sound if and only if, for any application of the rule, if the conclusion is invalid, then some premise must be invalid. So this statement, if the conclusion is invalid, then some premise is invalid, is the contrapositive of the defining statement shown on the top of the slide. So these two are easily shown to be equivalent, and when we prove rules sound throughout our discussion, we will be using this characterization of soundness, showing that invalidity can be preserved bottom up. And the reason why we do this is because it makes the proofs a little bit simpler. You can prove rules sound by talking about validity being preserved top down, but there is a case distinction that arises in some of the proofs. If we go with this characterization instead on the basis of invalidity, that case distinction disappears. So it just streamlines the proof a little bit. Now we define a calculus to be sound if and only if all of its rules are sound. And essentially what that means is that all of the axioms of your system are valid and all of the inference rules preserve validity, so anything that is provable in your system is going to be valid. Okay? So let's go about and discuss this nested sequent calculus now. So you might be familiar with axiom systems if you've taken a course in logic before, also called Hilbert systems. Typically in Hilbert systems, you have a large number of axioms and a small number of inference rules, like modus ponens or necessitation if you're dealing with a modal logic. In sequence systems, this is reversed. We have a small number of axioms and a large number of rules, which is why sequent calculi are very helpful for doing proof construction. And this is the sole axiom in our nested sequent calculus called the ID rule, which stands for identity. And essentially what it says in the notation that was introduced yesterday is that any nested sequent such that in the consequent at some component there exists a propositional atom in its negation is considered an axiom of the system. That's what this rule is saying. So this is technically a schema that is capturing an infinite number of nested sequents satisfying a certain property, which can all serve as axioms in a proof. And to demonstrate an instance of the ID rule, I've given two examples on the bottom of the slide. So here is an example of a nested sequent. It has two sharpening statements in the antecedent, and it has only a single component in the consequent. But you can see that it serves as an instance of ID because it has a propositional atom in its negation occurring. Okay? Here's a second example. It has an empty antecedent, and the consequent is a little bit more complicated. It technically encodes a tree of depth 1, where this is the root of the tree, and the child node contains Q and not Q. And because of that fact, this serves as an instance of the ID rule. Note that this P, which appears in the rule, is not a fixed propositional atom, but it's taken to be a metavariable. It just means some propositional atom. So it's fine if the propositional atoms which make it an instance of ID are different from P, so Q or R, for example. Okay, so let's talk a little bit about why this rule is sound. It's quite easy to show the ID rule sound. When you have a nullary rule like ID that has 0 premises and just lets you introduce a nested sequent in a proof, what it means to be sound is that any instance of it is valid. So to show this sound, what we're going to do is suppose for a contradiction that the conclusion of the ID rule is invalid. Right? And then when we derive a contradiction, we will know that any instance must be valid. Okay, by the definition of invalidity, if we have some nested sequent which is invalid, then it must be the case that there exists a model and a precisification in that model which falsifies the formula interpretation of that nested sequent. As we discussed last time, we take nested sequents to be equivalent to their formula interpretation. Right? So if a nested sequent is invalid, then its formula interpretation is invalid. Okay, so the next thing is we're going to make a small observation. We know that by the form of the ID rule, the nested sequent must have some propositional atom and its negation occurring in some component. Right? That's what this is saying here on the right-hand side of the sequent. And therefore, we know that P and not P either occur at the root component or in one of these child components inside one of these nestings. Now I'm just going to prove soundness in the first case, where P and not P occur in the root component of the consequent. The other cases are shown in a very similar way. So let's assume that the root component, denoted sigma naught, contains P and not P. Then using this line from above, that the formula interpretation is false on M at pi naught, we know that this formula, which is equal to the formula interpretation, is false on M at pi naught. So if you recall from yesterday, when we take the formula interpretation of a nested sequent, we form a conjunction with the antecedent, transform the sequent arrow into an implication, and then we form a giant disjunction with everything in the consequent. Now, since we know that P and not P occur at the root component of the nested sequent, we have them occurring here in this disjunction. And since this is an implication which is falsified, it follows that the left-hand side is true and the right-hand side, the consequent, is false. Therefore, this disjunction on the right-hand side is false. And from this, you can conclude that both P and not P must be false on M at pi naught, right? Which cannot happen in standpoint models, because the function delta essentially maps every propositional atom to some precisification, or it doesn't map it there. So either a propositional atom will be true or not true at a precisification. You cannot have this situation arising. This gives a contradiction, and what that means is that any instance of the ID rule is valid. So any nested sequent which satisfies this property is automatically going to be valid. Okay, so that was the ID rule. Let's now look at the next rule in our system, which is the disjunction rule. And the way the disjunction rule works is it takes a nested sequent where we have two formulae, phi and psi, occurring in some component in one of these multisets. And what the disjunction rule lets you do is it just lets you add a disjunction between these two formulae. That's the whole operation of this rule. Okay, so we can see two examples. Here's a nested sequent. We have P and Q occurring at the root component. And if we apply the disjunction rule, we can introduce a disjunction between them. Here's an example of another nested sequent where we have P and not P occurring in the same component, and we can introduce a disjunction between the two of these. So that is how the disjunction rule operates. It's very simple. And the soundness of this rule follows directly from the formula interpretation, since in the formula interpretation we interpret commas on the right-hand side disjunctively. So we'll show that on this slide. It's a very simple proof. To show this rule sound, right, we can assume that the conclusion is invalid. Now, if the conclusion of this rule is invalid, then obviously, by definition, the formula interpretation is invalid. And one thing that we can recognize, since commas are interpreted disjunctively on the right-hand side of nested sequence, the formula interpretation of the conclusion is actually identical to the formula interpretation of the premise. And so it follows then that the premise must be invalid as well. So the soundness of this rule is quite simple to show. Okay, let's now discuss the next rule in the system. The third rule in the nested sequent calculus is the conjunction rule. And the way this rule works, it's the only binary rule in the system, meaning it has two premises. The way the rule works is that if you are able to derive a nested sequent where you have in the consequent some formula phi appearing in some component, and you're able to derive an almost identical nested sequent, with the only difference being that psi occurs where phi occurs in the left one, then you can introduce a conjunction between the two. So to demonstrate this rule, again, there's two examples on the bottom of the slide. Here's a very simple nested sequent with a p serving as the entire consequent, and another nested sequent which is almost identical but with q instead of p. We can introduce a conjunction between p and q. Here's another example. We have in this example a single nesting as the consequent, and we have a p occurring inside of the nesting. And we have another nested sequent where we have a not p occurring instead. Well, if we apply the conjunction rule between these two formulae, we can obtain a nested sequent where we have p and not p occurring instead. Okay. And the soundness for this rule is a little bit more complicated than it was in the previous two cases. We'll go through it line by line so you can see why this is why this is a sound rule. So again, we're going to argue soundness by assuming that the conclusion is invalid and showing that at least one premise must be invalid. As I stated earlier, this is an equivalent characterization of soundness. So let us suppose that we have some application of the rule where the conclusion is invalid. Then by the definition of invalidity, there must exist a model and a precisification which falsifies the formula interpretation of the conclusion. And now we know that by the shape of this rule, phi 1 and phi 2 occur in some component in the consequent. So it could appear in the root component or in one of the children components in one of the nestings. I'm just going to make the assumption that it appears in the root component. The other cases are proven in a very similar fashion. Okay? What that means then is that following from this fact that we had already deduced above, we have that this implication is false on m at pi naught, which is equal to the formula interpretation iota applied to this nested sequent, which serves as the conclusion of the rule. And since we've made the case assumption that phi 1 and phi 2 occur in the root component, we know that we have phi 1 and phi 2 occurring together with some disjunction of formulae sigma naught prime. Now, we can start applying certain equivalences from classical logic to manipulate this formula. And the goal is going to be to try to obtain a propositional standpoint formula which corresponds to a formula interpretation of one of the two premises, which will then allow us to deduce that one of the two premises must be invalid. So what we're going to do first is apply the principle that disjunction distributes over conjunction. If we do that, then we can transform this disjunction where we have a conjunction of phi 1 and phi 2 into a conjunction of disjunctions. Right? We're just distributing this disjunction of sigma naught prime over phi 1 and phi 2. Then what we can do next is apply this distributivity property another time to distribute this n-ary disjunction of these box formulae over the conjunction on the left-hand side. Right? This is permitted as well in classical reasoning, and it gives us this very lengthy consequent in our implication, where we now have the n-ary disjunction occurring two times and now disjoined with the two previous conjuncts. Right? Okay, so we now have this very lengthy formula, which is false on m at pi naught, and it's an implication, right? So this means that the antecedent must be true at pi naught, and the consequent must be false. I've omitted m here just because the line is too lengthy and would go off of the slide. So we have that this giant conjunction is false at pi naught, which means, by the semantics, that one of the conjuncts has to be false, right? So that means that for some j equal to equal to 1 or 2, it must be the case that this implication is false on m at pi naught, because we have everything in gamma holding, and we have one of these conjuncts being false. Now this formula down here, when j takes the value 1, or serves as the formula interpretation of the left premise, because we have a phi1 occurring. And when it takes the value, when j takes the value 2, it serves as the formula interpretation of the right premise. So this establishes that one of the premises must be invalid. So we have soundness of the conjunction rule. Let's now move on to the more interesting rules with standpoint modalities. So what we'll discuss next is the box S rule. And this rule has a bit of a complicated functionality. What it says is that if I have occurring in a component somewhere in my consequent a box S phi formula, and it's also the case that in my consequent I have in S nesting with a phi occurring inside of it, then I am allowed to delete that nesting top-down. So essentially what this means is that this information is redundant. That's why it can be deleted. Now there is a side condition which is imposed on this rule for technical reasons which are related to proof search, something that I'll discuss later on in the lecture today, which says that this pi prime label which appears on this nesting must be fresh. This is imposed for, as I said, technical reasons. Essentially what happens is during proof search we apply rules bottom up to try to construct a proof of a given formula. And we need to ensure that the labels on nestings are always unique. And this helps ensure that. But this will pop up a bit later on in the lecture. For now, you can essentially ignore this side condition. Okay, so let's look at a couple applications of this rule. So the first example, we have a box S P occurring in the root component. And we have in S nesting, where P occurs. So it satisfies the form of this rule. We can therefore delete this nesting top-down. In the second example, we have a box SQ occurring in the root component. And we have this nesting occurring that's tagged with an S and has a Q inside of it. So it can be deleted top-down if we apply this rule. All right, let's go about and prove this rule sound so you can see why it makes sense. Again, the setup is the same as before. We assume that the conclusion is invalid, which implies the existence of a model and a precisification, such that the formula interpretation of the conclusion is false on M at pi naught. And again, we have a case distinction that arises. This formula in the conclusion, box S phi, can occur in either the root component or one of the child components. We'll only consider the case where it occurs in the root component, which I'm calling sigma naught. So underneath the assumptions and this case assumption, it follows that this formula, which is the formula interpretation of the conclusion, is false on M at pi naught. And we have this box S phi occurring in this part of the disjunction since we've assumed it occurs in the root component. Now in classical logic, the disjunction connective is idempotent, as it's called, which means that phi or phi is equivalent to phi in classical logic. So that means that I can extend this box formula to be disjoined with itself. Right? So this disjunction is equivalent to just box S phi. So I'm allowed to add this extra box formula. And we additionally have in classical reasoning, which this is a classical logic we're dealing with, that the disjunction connective is both associative and commutative. This means that if I have some n-ary disjunction, I'm always free to move the disjunctions around to whichever position in the disjunction that I so choose. So I can move this disjunction here over to the end. And what happens is this formula, which is falsified on M at pi naught, perfectly pattern matches the formula interpretation of the premise, right, where this nesting would be interpreted as this box S phi occurring here. Therefore, we have that the formula interpretation of the premise is false on M at pi naught and is therefore invalid. Right? So that proves the soundness of this particular rule. Okay. The next rule that occurs in our system is called the non-emptiness rule. So we technically have this rule for every standpoint that appears in our vocabulary. And this rule is called the non-emptiness rule because it's encoding the fact that when we interpret standpoints, there is always at least one precisification in their interpretation in a model. And when we look at the soundness proof on the next slide, that will become quite apparent because it's used to establish the soundness of this rule. The way this rule works is it allows for you to take a nested sequent where you have a nesting tagged with an S, and if there's an empty set occurring inside of that nesting, you can just delete it. Okay? This also has the same side condition as the box rule imposed on it, which is that pi prime must be fresh. What that means is that the tag pi prime is distinct from all the other tags on nestings occurring in delta. And again, this is just a technical matter that relates to the proof search algorithm we'll discuss later on. So you could ignore it for the time being. Here's an application of this rule. Right? We have a nested sequent where we have a nesting occurring with the tagged with an S and where there's an empty set on the inside, and we can just delete it top down. And here's a second example of applying this rule where we have this particular nesting with an empty set on the inside that can be deleted top down. Okay, so let's look at the soundness of this rule. Again, the setup is the same. We assume that the conclusion is invalid. Therefore, there's a model and a precisification in that model which falsifies the formula interpretation of the conclusion. Now, this means that the following formula is false on m at pi naught by the definition of the iota function, the formula interpretation. And now we're going to make an observation to manipulate this formula and transform it into the formula interpretation of the premise, just as we did in the previous cases. We observe, as I had said just a moment ago, that the interpretation of every standpoint is non-empty. And therefore, there has to exist some precisification inside of the interpretation of S, or there just has to exist a precisification in the interpretation of S. And what this implies is that in our model, at pi naught, we have the following formula being satisfied, diamond S top. Diamond S top says that there exists some precisification in the interpretation of S such that top holds, which is equivalent to just saying that there is some precisification in the interpretation of S. So if this formula is satisfied in M at pi naught, then its negation is obviously not satisfied by the semantics of standpoint logic. And if you recall from yesterday's lecture, with the full negation operator, which we've defined, it gets pushed inwards, and that then establishes that, or implies that box S falsum is false at m at pi naught. Now, since this is falsified in m at pi naught, we are free to put it into the conclusion of this implication, and it will keep the implication false if we do that, right? Because an implication is false when its antecedent is true and everything in its consequent is false. Now, this formula serves as the formula interpretation of the premise, where box S falsum is what we get when we transform this nesting into a formula, and therefore we have established that the premise is invalid. So this is likewise a sound rule in our nested sequent calculus. Next, we're going to talk about the diamond rules. There are 3 diamond rules that appear in this nested sequent calculus. The first 2, this one and the next one we will discuss, have a bit of a complicated functionality because they have a slightly complex side condition which ensures soundness of the rule. So let's try to unpack this rule and see what it says. The way that the diamond rule works is that it says that if we have a nested sequent where there is a diamond formula occurring in some component of the form diamond S phi, and we can find another component tagged with an S prime, a different standpoint, and containing phi, then if it is the case that this S prime and this S stand in some relation to each other, which I'll explain momentarily, you can delete this phi top down. It becomes redundant information. So what is this side condition that is imposed on this diamond rule? What this side condition does is it takes the antecedent of our nested sequent. Note that up until this point, none of the rules that I've introduced have relied on any of the information in the antecedent, the sharpening statements. This rule does make use of this information. And what this relation does is it essentially computes all of the sharpening statements that hold between standpoints based off of the information in the antecedent of the nested sequent. And the way it does this computation is explained here in this definition. So I'm going to refer to this as the antecedent relation. And this antecedent relation, which serves as a side condition in this rule, is a binary relation over our set of standpoints. And it is the minimal, reflexive, and transitive relation which satisfies these two conditions. The first condition says that if there is a sharpening statement occurring in my antecedent, then the standpoint S and T must stand in this antecedent relation to each other. And the second condition says that for every standpoint in S, it must stand in the antecedent relation to the universal standpoint. So to try to make this definition more comprehensible, I've given an example on the bottom of the slide. If we assume that our set of standpoints contains 3 or 4 standpoints, S, S prime, T, and the universal standpoint, and we also assume that our antecedent in a rule application contains these 2 sharpening statements, then we can compute this binary relation as shown on the bottom of the slide. So first, we have, by this clause of the definition, that S must stand in the antecedent relation to S prime, and S prime must stand in the antecedent relation to T, given this information in gamma. We have also that this relation is reflexive, so this gives rise to all of these relations holding, and every standpoint must relate to itself via this antecedent relation. This is also a transitive relation, so since we have S seeing S prime and S prime seeing T via this relation, S must see T. And last, we have this universal condition, which is imposed, which says that every standpoint must relate to the universal standpoint, which makes sense because the universal standpoint subsumes all others. And that gives rise to these 3 pairs holding in this relation, where this technically could be computed as well according to the universal condition. And since this is a minimal relation, it means that there are no other relations that are going to occur. So this just gives an example of how this relation is computed. And whenever you apply the diamond rule in the proof, and also the next diamond rule that we'll discuss, you always need to compute this relation to make sure that the rule application is sound, to make sure that this S tagging the diamond and this S prime tagging the nesting stand in this relation to one another. Okay, so let's look at 2 instances of the rule. We have an application of the rule here on the left. We have this diamond SP occurring in the root component of this nested sequent. We have an S nesting, and we have a P occurring inside of that S nesting. Now, by the reflexivity condition on this rule, S relates to itself. Therefore, I am free to apply this rule and delete this P top-down in this rule application. Here's another example of this rule. I have an S prime being sharper than S occurring in the antecedent. I have an S diamond P occurring in the root component. And then I have a P occurring in an S prime nesting. Now, since S prime is sharper than S, then since this antecedent relation inherits the relations from the antecedent, S prime stands in the antecedent relation to S, so I can delete this P top-down. Now, I'm not going to prove this rule sound like I did the last ones. The reason why is that there are some auxiliary lemmas that one needs to show on the basis of this side condition, but you can find that information on the course webpage in one of the links for this material. Okay, there's a second diamond rule that appears in our system, which also has the same side condition imposed on it. It has a slightly different functionality. In the last diamond rule, we had the diamond formula appearing in a different component than the component where the formula phi was deleted. In this rule, they appear in the same component. So the way this rule works is that if I have a diamond S phi occurring in a child component along with a phi, and I have that same relation holding between S prime and S, then I am allowed to delete this copy of phi top-down in a rule application. Okay? So here's an application of the rule. I have diamond SP occurring inside of an S nesting, and I have a P occurring as well. Since this antecedent relation is reflexive, as we discussed previously, I can delete this P top-down in a rule application. Here's another example. I have diamond SP occurring in an S nesting with a P, and I have S prime being sharper than S in the antecedent. Therefore, this relation holds. Since the side condition holds, I can delete this P top-down. Likewise, I will not show this rule sound because it relies on these auxiliary lemmas, which would take too much time to go through. The very last rule in our system is the diamond star rule. So this is used exclusively for the universal standpoint. And what this rule says is that if I have a universal standpoint diamond formula occurring in any component, And the formula phi, which occurs in its context, occurs in the root of the nested sequent. That's why it's on the left of the delta. Then I am allowed to delete that phi. And there are two applications of the rule shown here. Right? Here I have the universal diamond P occurring in the root component together with P. It satisfies what the shape of the premise of this rule, so I can delete this P going top down. As another example, I have a universal diamond P occurring inside of this nesting here. I have a P occurring at the root component, so it can be deleted top down. And this rule can be shown sound as well. And the proof is a little bit simpler than the previous two, but still I'm going to skip it for time reasons. Okay, so we have that all of the rules in our system are sound, and therefore the nested sequent calculus is sound by the definition I gave earlier. What I'm going to do now is discuss proofs and derivations. So proofs and derivations are two different kinds of constructs which are built in the system using inference rules and nested sequence. So I'll give an example of a proof first on this slide. The rules that are used in this proof are shown on the top of the slide for reference. And I'll explain how the proof is built via these rule applications in a bottom-up fashion. So it might seem a bit counterintuitive because we typically read proofs top-down from the axioms or instances of ID to the conclusion. But oftentimes in proof theory, it's much easier to build proofs starting from the conclusion and working our way upwards towards the axioms. And that's actually how proof search works as well, as we'll see in the next part of this lecture. So I'm going to establish that this formula is a validity of propositional standpoint logic by constructing a proof for it. And remember that the implication connective is defined in our language. Our language is technically a language in negation normal form, so this formula shown here is equivalent to this formula when we take, or it's actually equal to this formula since we take implication to be defined. Okay, so let's look at how a proof is built. It's built by just applying rules bottom up until you reach the ID instances. So as a first bottom-up step, we can break apart this disjunction by applying the disjunction rule. Right, so that's just applying this rule, which says that if I have a disjunction appearing, I can break apart the disjunction and have each disjunct fused together with a comma operator. I now have two choices of a rule that I could apply next. I could apply, for example, the universal standpoint diamond rule or the disjunction rule. I'm going to apply the disjunction rule to break apart this P or Q. And then next, I'm going to process this universal standpoint diamond. This rule says, right, that if I have a formula of this shape occurring anywhere in my nested sequent, then I can introduce the formula that occurs within the context of the diamond to the root of my nested sequent. So if I apply this rule bottom up, it introduces this not P and not Q. And next, I can apply the conjunction rule bottom up and break this conjunction apart into two different nested sequents, a left one which contains the left conjunct not P, and a right nested sequent which contains not Q. Now, we can see that this nested sequent is an instance of ID, so this proof procedure that I'm explaining halts. We have a P and a not P occurring, and in the right premise, we have a Q and a not Q occurring, therefore it's an instance of ID as well, and the proof process stops. So this also gives some information into how proof search works. This is how the algorithm is going to construct proofs in this bottom-up manner. And since our system is sound, this witnesses that, or gives an argument as to why this theorem, which is established as the conclusion of the proof, is of validity. Okay, let's talk next about derivations. So derivations are like proofs, but their leaps or initial sequence at the top of the proof do not have to be instances of ID. So these are more general structures. And technically speaking, when we do proof search in a sequent calculus, we construct derivations with the hope that they will become a proof. That's kind of the idea. So I'll give an example of how this derivation is built and also give explicit definitions on the next slide of derivation and proof to try to make it as comprehensible as possible. So let's construct a derivation of this particular formula. We would apply the disjunction rule. We could apply the disjunction rule first, which gives these two formulae fused together with a comma now. So essentially when we replace the disjunction with a comma, it means that operator's been processed. We can now apply the universal standpoint diamond rule to introduce a P to the root component. And we can apply a conjunction rule to break this conjunction apart, giving us a not P in the left premise and a not Q in the right premise. Now, the left premise is an instance of ID, so we can close the branch there of the proof construction process, but the right premise is not instance of ID. And in fact, if we were to try to continue searching for a proof by bottom-up applying rules to this nested sequent, the only rule that would actually be applicable is the universal diamond rule, and it would just keep introducing P's, so the process wouldn't halt. So that establishes that this is actually not a theorem of standpoint logic. And I'll make this fact more precise a bit later on. Okay, so in our nested sequent calculus, we define a derivation to be a tree of nested sequence such that every parent node is the conclusion of a rule application with its children, the premises. If we look at the previous slide, this gives an example of a derivation. It's a tree-like structure of nested sequence where the edges are thought of as these inference lines. We have sometimes a single child, or we might have leaves, or we might have two children. And essentially, this tree-like structure respects the rules of the calculus. A proof is a special kind of derivation such that every leaf is an instance of ID. And so we saw that on this slide. Every leaf of the tree-like structure was an axiom. So that's the difference between derivations and proofs. Sometimes these two terms are used synonymously in the literature, but it's becoming more normal to separate these two notions. So derivations are a proper proofs are a proper subclass of derivations. And as I said before, our nested sequent calculus is sound, which means that if a proof exists for something, then it is valid. Okay, next we are going to discuss decidability of propositional standpoint logic by means of a proof search algorithm. And this material is a little bit complicated, but I'll try my best to explain it at a high level. So a decision procedure is a type of algorithm that terminates and decides if a formula in a logic is valid or invalid. Or you can also rephrase this as deciding if a formula is satisfiable or unsatisfiable. A proof search algorithm is a special type of decision procedure. There are a lot of different kinds of decision procedures. For example, classical propositional logic, you can just use truth tables as a decision procedure. In a proof search algorithm, what we do, as I've alluded to before, is we take a formula as input and we bottom-up apply rules from a calculus to it with the goal of trying to construct a proof. So in our case, what will happen is we will take a nested sequent as input, and we will apply rules bottom up to this nested sequent. And if we are able to construct a proof, then the proof search algorithm will terminate and will output the value valid or true because we have a proof of the input, so we know that it is in fact valid by the soundness of the proof system. And then we will have to come up with certain termination conditions that I'll discuss over the next couple slides to determine when we should stop applying rules and when an ID rule will not be achieved along some branch of the proof search. And in that case, the proof search algorithm will stop and will output the value invalid or false, and we will show that the concluding nested sequent can be provided a counter model in that case. So that's essentially the way that the proof search algorithm works. And when we have these proof search algorithms, there's various questions that we have to answer to ensure that they worked correctly and as we would like. So we oftentimes need to show termination of these proof search algorithms. We'll be able to prove this in our case. Once you can establish termination of your algorithm, you also want to do things like analyze the complexity and make sure that it does not use a lot of time resources or space resources. In the case of propositional standpoint logic, we will see that our algorithm runs in coNP, which is the best that we can do for this logic. And another interesting aspect of proof search algorithms, which is distinct from other kinds, is that we oftentimes get, when proof search terminates, certificates, or explanations as some people call them, which explain why some sequent or formula is valid or explain why it is invalid. Okay, so let's talk a little bit about proof search in the nested sequent calculus and the issue that arises with termination. So I alluded to this before with the example of the derivation, where along the rightward branch we could just keep applying the universal diamond rule bottom up ad infinitum. And what this means is that to ensure the termination of our algorithm, we're going to have to come up with a set of criteria or conditions such that when branches and derivations satisfy these conditions, we can safely stop the proof construction process or proof search process. So here's an example of a problematic proof search. If we do not have conditions imposed, termination conditions imposed, then we could, for example, take this particular nested sequent, and if we apply, for example, the universal diamond rule bottom up, then that would introduce this box star P, and applying the box star rule bottom up would introduce this component with a fresh label P1. I could then apply the diamond 1 rule to introduce a box from here into this component. And what would happen in that case is that I could apply the box rule again to introduce yet another nesting, another component in my nested sequent, which has a P. And I can just repeat this process ad infinitum, constantly growing this nested sequent with more and more children in the consequent. So we need to come up with information, or we need to come up with conditions that tell us when to stop this proof search. And the conditions that are used in proof search algorithms for sequent calculi are typically called saturation conditions. And what these conditions do is they tell you that a rule has already been applied to a formula in a satisfactory way and need not be applied again. And as we'll see over the course of the next couple slides, this sequent right here that I've highlighted actually satisfies these saturation conditions, and you can stop the proof search procedure once this sequent is reached. So the saturation conditions are a little bit complicated. They're on this slide, but we'll go through them, and I'll give an example of these saturation conditions applying to a nested sequent. So a nested sequent is determined to be saturated if and only if, for all of its components, the following conditions are satisfied. And these saturation conditions have names which are very similar to the names of the rules. That's not a coincidence. Essentially, these saturation conditions ensure that a rule is no longer meaningfully applicable to a particular component of a nested sequent. So the ID condition says that if we have a propositional atom occurring in within not a nesting but a component, then its negation must not occur there. If we have the disjunction condition says that if we have a disjunction occurring inside of a component, then it's the case that both disjuncts already occur there. Recall that the disjunction rule, when we applied it bottom up, it broke the disjunction apart. So it would break phi or psi apart and introduce a phi comma psi in the antecedent. So if a component already has these two disjuncts occurring, there's no need to apply the disjunction rule to a disjunction appearing in a component. So this is recognizing the redundancy of such a rule application. The conjunction condition is kind of similar. So it says that if I have a conjunction in a component and one of the conjuncts already appears there, there's no need to apply the conjunction rule anymore. We have a rule for the diamond operator where the standpoint S is not the universal standpoint. So this says that if I have a diamond S phi occurring in a component and I have this side relation holding, the antecedent relation with S and S prime, then it must be the case that phi has been introduced to sigma j, the component sigma j, which has an S prime as its tagging its nesting. The universal diamond condition says that if I have a universal diamond phi occurring in some component, then phi must occur in the root component. So this is suggesting that the universal diamond rule does not need to be applied. And then we have rules for the boxes and the non-emptiness rule. So the box S saturation condition says that if I have box S phi occurring in a component, then it must be the case that there is some other component already containing phi. And last, the non-emptiness condition, which says that for every standpoint, there must be some nesting that occurs, which is tagged with that standpoint S. Okay? So it's not important to understand all of these in complete detail, just that essentially these demonstrate that a nested sequent, if it satisfies these properties, can be transformed into a counter model and also can be used to halt the proof search algorithm. So that's what I'm going to show on this slide. This is the nested sequent, which came from the example a couple slides ago. So this nested sequent here. And this nested sequent satisfies these saturation conditions. And as I'll show on this slide, it can be transformed into a model which falsifies this nested sequent, which was the conclusion of this derivation. Okay? And that's the importance of saturated nested sequence. They can be transformed into models which falsify the input of your proof search algorithm. So how do we transform it into a model? What we do is we treat all of the components in the nested sequent as a precisification. So the number of components is equal to the number of precisifications in the model. We think of the root component as giving rise to a precisification pi naught. And then this nesting, which is tagged with a pi 1, becomes the second precisification pi 1. Okay? This also shows how these labels which are used on nestings are used. They're used to help us define this counter model in proof search. Now, in this model, we define, of course, the universal standpoint to be equal to all of big pi, as usual. And we then define the delta function, which interprets our propositional atoms, as shown here. Essentially, a propositional atom is taken to be true at a precisification if it does not occur in the component that relates to that precisification. So we have, for example, p not occurring in the root component of the nested sequent. Therefore, we take p to be true there. But we do have p occurring in this child component, so we take p to be false there. If we define the model in this way, then it will serve as a falsifying model of this input. So here's a visual representation of this model, which is extracted from this saturated sequent. And we can verify, as shown on the right, that it does in fact falsify this formula. So we first of all have at pi naught that the universal standpoint box P is falsified. The reason being that this formula is saying that everywhere inside of my model, P is true, but that's obviously not the case because P is false at pi 1. We also have that this formula is false at pi 1 because, again, it's saying that everywhere in my model, P is true, but that's not the case because of pi 1. Therefore, there is not a single precisification which satisfies this formula in this model, so we have that this formula is false in the model at pi naught. So this is really the key idea of proof search. You build a derivation, and if you find a proof, you say, yes, my input's valid. And if you fail to find a proof, you will eventually generate a saturated sequent, which can be turned into a model to falsify your input, meaning that it is invalid. So here is a very high-level description of the proof search algorithm for standpoint logic. And the actual algorithm diverges a little bit from the algorithm I described earlier, in that there are some modifications made to it to ensure that the algorithm is as efficient as possible, that it works in the complexity class coNP. So essentially, the way the proof search algorithm works is, in this setting, is that to obtain coNP complexity, is that we take a nested sequent as input, and we start applying rules bottom up. And once we hit a conjunction rule, then we non-deterministically choose either the left premise or the right premise. And we continue this process until we hit a saturated sequent or an instance of ID. What this means is that this proof search algorithm makes non-deterministic guesses when conjunction rules are reached, and it only builds a branch of a derivation at a time. If all of those branches that are built terminate at instances of ID, this will imply that a proof exists, so the input's valid. And if one of those branches terminates at a saturated sequent, then, as we saw from the previous slide, that will imply that the input is invalid. So proof search is done in a very special way where we are really only generating parts of the proof at a time in order to obtain optimal complexity. So I've already talked a little bit about what happens when proof search fails a couple slides ago. When a saturated sequent is generated, then it falsifies the input. Let's talk now about what happens with successful proof search in this very special case where only branches are generated at a time. So I'm going to explain this by means of an example. Let us suppose that this algorithm that I just described takes this standpoint formula as input. Since this is a non-deterministic algorithm that non-deterministically chooses premises of the conjunction rule, what would happen if I plugged this into the algorithm just described is it would choose either the left conjunct or the right conjunct to continue building a branch in a derivation. So let's suppose that it chooses the first conjunct. If it did that, then what would happen next is it would continue building the branch. So it would apply, for example, the box rule, which would introduce this nesting bottom up. It would then apply the disjunction rule, since that's applicable, which would then give rise to these two formulae in this nesting. And once again, we've hit a conjunction, so it non-deterministically picks a conjunct. Say it picks the left one, then that gives you this particular nested sequent. Since ID was reached, outputs true or valid, and proof search stops along this branch, which is one of the non-deterministic choices. Now, based on these non-deterministic choices, we can build, or we can obtain different branches. So it could be the case that proof search proceeds in almost the same fashion, but instead, at the end, instead of picking the left conjunct, we pick the right conjunct. Again, this would give an instance of ID and return true. And the third branch, which could be built for this formula in our non-deterministic algorithm, is the following. Instead of initially picking the left conjunct, it picks the right conjunct, and it continues proof search with that. So it would bottom-up apply, for example, the non-empty rule, introducing this nesting. We could then apply the diamond S rule to introduce this Q or not Q into this nesting, and then break this disjunction apart to obtain a Q or not Q in the premise, which is an instance of ID. So what has happened in this particular example is that every non-deterministic choice led to a successful branch, and you can take all three of these branches and sort of zip them together, fuse them together at these dashed lines to build this proof in the nested sequent calculus, which witnesses that the formula phi, the input, is in fact valid. So that's the way that this proof search algorithm actually works in order to obtain coNP complexity, right? So it's a bit complicated, but it's very efficient. Okay, so we have, on the basis of this algorithm, completeness, or correctness, which establishes soundness and completeness of the algorithm. If the algorithm returns true for every non-deterministic choice, then all of these branches end at instances of ID, and you can show in general that you can always zip these branches together and build a proof so that witnesses that the input was in fact valid. This phi should be a delta, by the way, so that's a typo. And if it returns false, then one of these non-deterministic choices, one of these branches that was built, yielded a saturated sequent. And as I explained earlier with an example, that can be used to build a counter model of the input. So that means that the input is invalid. So we have soundness and completeness of the algorithm, or correctness, as it's called. And one can also show termination, that each of these branches, which are built based on these non-deterministic choices, are only polynomially big in terms of the size of the input. So this gives a coNP algorithm. Okay, so there are a few corollaries of proof search. I established soundness of the nested sequent calculus earlier by showing that all of the rules were sound, but we actually didn't prove completeness. It turns out that completeness is a corollary of the proof search algorithm. The proof search algorithm gives completeness, because if a nested sequent is valid, then if you plug it into the algorithm, it will find a proof of it. It has to, by the correctness theorem. So that gives completeness of our system. So we have a sound and complete system for standpoint logic. We also have the so-called small model property. One can show that these falsifying models, when a formula is invalid, are actually quite small. So the falsifying models will only contain, the number of precisifications they contain will be bounded by 1 plus the number of standpoints in your language, and also bounded by the length of the formula phi, which was the input formula to your algorithm. And the length, by the way, of a formula is defined to be the number of symbols that it contains. This small model property can actually be improved via semantic arguments. So one can show that in propositional standpoint logic, in order to satisfy a formula or falsify a formula, you only need to have a model with, at most, size of phi many precisifications, where this is the formula that you're trying to show satisfiable or invalid. And as I said a few times already, the complexity of this algorithm is coNP, which means, so the validity problem is in coNP, and the satisfiability is in NP. Okay, so what we're going to talk about next is first-order standpoint logic. I think this is a good time to take a 5-minute break. So let's reconvene at 10 o'clock, and then we'll talk about first-order standpoint logic after. Okay, let's continue. So we've just gone over propositional standpoint logic. We looked at the syntax, the semantics, and we also looked at an algorithm for deciding the logic, which gave us some interesting corollaries, told us about the complexity of the logic, as well as showed that the logic had this small model property. What we're going to talk about next is an extension of propositional standpoint logic called first-order standpoint logic, or FOSL. And this is a very expressive logic which has a lot more modeling capacity. So it's quite evident that the language of propositional standpoint logic forgoes the inclusion of certain constructs which could be useful in knowledge representation. For instance, propositional standpoint logic does not include combinations of standpoints. So this is one way in which we could increase the expressivity of our language. For example, here, this shows that from standpoint LC and standpoint LU, some fact holds. So first-order standpoint logic will include expressions like this. And we can also add, for example, quantification. This is something that the propositional setting does not include, universal and existential quantification, where we can say, for example, that for all x, two standpoints have the same interpretation, for example, of what it means to be a clearing. Additionally, in the propositional setting, we do not have constant symbols which name entities, we do not have variables, and we do not establish relationships between them. So in FOSL, we're going to rectify this to give a very expressive standpoint language, and the remaining logics that we will look at throughout the remainder of the course will be fragments of this language, which are decidable. This language itself is not. Okay, so we'll include predicates and quantifiers in our language, and we're also going to include in modalities these complex standpoint expressions. Since standpoints are interpreted as types of sets, it makes sense to be able to define these and include these. So we will have in first-order standpoint logic the universal standpoint, again, single standpoints as we had before, but we allow for ourselves to take unions of standpoints, intersections between standpoints, and also the set difference of standpoints. So let me define this language for you formally. In the propositional setting, our language was defined relative to a vocabulary. Here, since we're dealing with a more expressive language, we're defining it relative to what's called a signature. The signature is a triple, which consists of three elements, P, C, and S. P is a set of what are called predicate symbols. Each predicate symbol has associated with it an implicit arity. This means that these are the number of arguments the predicate symbol can take. So if it's of arity k, then it establishes or represents a k-ary relation between objects. We also have in our signature constant symbols. These will be used to denote specific entities in a domain, so to name objects directly so that we can talk about them. And S contains standpoint symbols just as before. And some finite set contains ST, maybe these are primed, and it also contains the universal standpoint. Note also that within our language, which I'll discuss below, there are variables which occur. This is not a member of the signature, but this is an aspect of the language. But I'll talk about that a little bit later. Okay, as I said on the previous slide, we have within our language these standpoint expressions, as they are called, which are essentially just set operations over standpoints, and these will be used to index modalities rather than just atomic standpoints, as we had in the propositional setting. The language of first-order standpoint logic is defined by this BNF grammar, shown on the bottom of the slide. So in the base case, we take atomic formulae to be FOSL formulae. So if P is a predicate of arity K, then it will take K, it takes K terms as its arguments. And essentially what this is expressing is that these terms stand in relation P to each other. And terms are defined to be either constants, which occur in the signature, names of entities, or variables, which will either be quantified or will vary over objects in the domain. We also have full negation in this language, so this is different than the propositional setting where we use negation normal form and only atomic negations. We have conjunction within our language, universal quantification, which says that for all x, some proposition phi holds, and we have finally our standpoint modalities. So we have, what this essentially says is that from complex standpoint E, it is unequivocal that phi holds. Okay? Where complex standpoint E, I'll explain how that's interpreted later on. As before, we also can take a lot of our logical operators to be defined. So top and falsum can be defined as before, relative to propositional atoms. Propositional atoms, by the way, are included in this language. It's just that when our predicate has an arity 0, it serves as a propositional atom. We can have disjunction defined in the normal way, since it doesn't appear in the language. And we define the existential quantifier, as one normally does, as being the dual of the universal quantifier. We can take diamonds to be defined as well. And last, we can also take the sharpening statements to be defined. So while these were needed in the propositional setting due to a lack of expressivity, we can define these by means of a complex standpoint expression, which is labeling a box. Essentially, what this formula says is that if I subtract standpoint E2 from standpoint E1, then a contradiction holds. So this is tantamount to saying that E1 is sharper than E2. Yes? These are not standpoints. These are taken to be terms that will refer to objects. So it's not, I guess I have to repeat the question. The question was, is P of T1 through Tk a relationship between standpoints? And the answer is no. This is a relationship between constants and variables. Yeah. Okay, so this is the language of first-order logic, and we will talk about how it is interpreted now. So similar to how first-order logic is interpreted, it's interpreted over certain kinds of structures, and we refer to these structures in this setting as first-order standpoint structures. These are quadruples denoted by M, which contain 4 different entities. The first is called the domain. So this is a non-empty set of objects. And this domain contains the objects that we will be speaking about with this language. Okay, so these are, for example, constant symbols are going to name objects in the domain. We have, as in the propositional setting, a non-empty set of precisifications, right, which are taken to be these points where language is made precise in a complete and consistent way. The sigma function is as before. It interprets standpoints to be sets of precisifications. There is one minor modification, which is that in the first order setting, it need not be the case that a standpoint has at least one precisification in its interpretation. So this is different than in the propositional setting. So you can map a standpoint to the empty set here. And last, we have this lambda function. And what the lambda function does is it maps each precisification to what's called a first order or classical interpretation over delta. So if anybody's taken a course in first order logic before, you'll note that you interpret predicates, k-area relations, and constant symbols over a domain. So you interpret constant symbols as elements in that domain, and you interpret predicates as relations over that domain. So what this lambda function is doing is it's taking a precisification and it's associating with it one of these interpretations. That's interpreting the constant symbols and the predicate symbols. I'll give an example of this on the next slide to try to make it clear. There are certain constraints that are imposed on these models. As always, the universal standpoint has to be the entire set of precisifications. We also have that these are technically constant domain models. What that means is that from all precisifications, you're making use of information from the exact same domain delta. So the domain does not change when you go from one precisification to the next. And also there is a rigidity condition which is imposed on constants. Essentially what this condition says is that if I interpret a constant to name a particular element in a domain at one precisification, then it will represent the same entity in a different precisification. So constants are constant between all the precisifications. So let's look at an example, because I think that's helpful for understanding the definition. So here we have an example of a model which has delta, pi, sigma, and lambda. The domain delta contains two objects, which I'm calling O1 and O2. Pi, the set of precisification, contains three precisifications, pi 1, pi 2, and pi 3. And in this model, we interpret S to be this, say, purple oval, which contains pi 1 and pi 2. We interpret the standpoint T to be the green oval containing pi 1 and pi 3. And as always, the universal standpoint just contains everything. And now we have, associated with each of these precisifications, a first-order interpretation of the constants and predicates, which is partially represented in this example. So we can interpret, for example, the constant A to be the object O1, and it will take that interpretation at pi 1, pi 2, and pi 3 due to the rigidity condition. And we can interpret, for example, the constant B to be O2, for example. So the constant symbols, their meaning is fixed throughout this entire model, but the predicates can vary. The way that predicates are applied varies, which relates to the philosophy I talked a bit about yesterday, supervaluationism, and how standpoint logic is about how we are applying terms to objects. So we have, according to this lambda function, that P is interpreted to be a property that's only true of O1 at pi 1. That's why we have the formula P of A being true of there, but it's not the case that P is true of B. We have that at precisification pi 2, the predicate P applies to nothing, so that's why it's the case that for both A and B, which are naming these objects, P does not hold. And we have that at pi 3, P holds of both O1 and O2, so that's why P of A is true and P of B is true there. So you can already see that what happens is that the lambda function, by associating a first-order interpretation with a precisification, tells you how to interpret formulae as being true or false at those precisifications. So that relates to what I'm going to discuss on this slide, which are the truth conditions for FOSL. Okay, so these are somewhat similar to the way that truth conditions are determined for first-order logic, with a little bit of modal semantics thrown in. So in order to interpret a first-order standpoint formula, we have to not only interpret it relative to a model and a precisification, like we did in the propositional setting, but we also have to define truth relative to what's called a variable assignment. The reason being that first-order standpoint formulae can contain free variables. So we need to know what these denote in order to interpret a sentence as true or false in a particular setting. So a variable assignment, all it does, it's a function denoted by little v, and it maps a variable to an element in the domain delta. Now, using this variable assignment, along with the lambda function, we have this piece of notation is technically a function which takes a term t, and if that term is a variable, it interprets it as v applied to x, and if that term is a constant symbol, then it interprets the term according to the lambda function. Okay? So that's all this notation is saying, is that if my term is a variable, I interpret it according to the variable assignment, and if it's a constant, I interpret it according to the lambda function. Okay, we interpret standpoint expressions in the expected way. So as always, the universal standpoint is just the set pi, and if we have a standpoint expression that unions to complex standpoints, then these are interpreted by taking the interpretation of E1 and the interpretation of E2 and unioning them together. And so the sigma function is working recursively here. Or if we have an intersection of standpoints, this is interpreted as taking the intersection of the interpretations. And similarly, the interpretation of the difference of standpoints is obtained by taking the difference of the interpretations. So this will play a role in this clause down here, in particular right here, where we're interpreting standpoint modalities. Okay, let's go through the notion of satisfaction now over these models. Okay, as I said before, the FOSL formulae are interpreted relative to models or structures and a precisification and a given variable assignment. So an atomic formula is going to be considered true relative to m, pi, and v if and only if the interpretation of all of the terms, which could be variables or constants, gives rise to a k-tuple which actually stands in relation p according to lambda. So this is the base case of determining truth. We have that the negation of a formula is true if and only if the formula is not true relative to m, pi, and v. We have that a conjunction is true relative to m, pi, and v if and only if both conjuncts are true relative to m, pi, and v. And then we have universal quantification, which makes use of this little bit of notation here, v, where I have this set brackets and x going to delta. Essentially what this is saying is that for all x phi holds relative to m, pi, and v, if and only if, when I take phi, which can contain the free variable x, if I let x vary over all of delta, so if I let x be the name of any object in delta and phi holds, if that's the case, then that means that phi holds of everything. So I can claim for all x phi. That's what this clause is saying here. And then we have the interpretation of standpoint boxes. So this says that from complex standpoint E, it's unequivocal that phi, if and only if, as before, according to all precisifications in the interpretation of complex standpoint E, phi holds. So this is just like it was in the propositional setting, the only difference being that we are defining this relative to complex standpoint expressions. Now, we also have global satisfaction notions that are defined in the semantics. So for example, if we write phi is satisfied relative to m and pi, then that is equivalent to saying that it holds regardless of which variable assignment you are using, v. And if we write that phi is satisfied on m, then that means that it holds regardless of not only every variable assignment, but also every precisification. So it holds everywhere inside of your model. And a formula is valid if and only if it holds in every model. Okay? Similar to before. Okay, so that was a quick little introduction to first-order standpoint logic, the language and the semantics. As I mentioned at the beginning of this section of the talk, the language of FOSL is undecidable. So we need to try to find fragments which can help us recapture decidability. The sentential fragment is not on its own decidable, but it allows for us to find decidable fragments, which is why it is quite helpful. And I'm going to talk about this now because a lot of the languages that Hannes will talk about in lectures 3 and 4 can be seen as fragments of this sentential fragment of first-order standpoint logic. So a first-order standpoint formula is called sentential if and only if it satisfies a certain property. That property being that if we look at any subformula of phi, which is a box formula, and all of the formulae occurring in psi, all of the variables occurring in psi, are bounded by a quantifier. None of them are free. That's what it means to be sentential. You never have it being the case that there's a free variable in the context of a standpoint modality. If you have this property, then it allows for you to use relatively small models to determine satisfaction of formulae, which is helpful from a complexity perspective, as I'll talk a little bit more on momentarily. Okay, so let's give a couple examples of sentential and non-sentential formulae to try to make this definition more concrete. So we have an example of a sentential formula here. Right? This formula has as its only box subformula itself. And if we look at the formula inside the context of that box, it does not contain any free variables. All of them are quantified over. Here's another example of a sentential formula. And it has this as its only box subformula. And we can see that none of its subformulae contain any free variables. This universal quantifier applies to both this x and this x, by the way. Here are some non-examples. So here is a first-order standpoint formula. We can see that if we look at its box subformula, there's only one in this case, that x serves as a free variable, so it's non-sentential. It doesn't have this syntactic property. Here's another non-example. It has two box subformulae, but both of them are identical and contain a free variable x in their context. So the reason why this property is useful is in part because it gives us what is called the small model property. That is expressed as a theorem on the bottom of the slide. And I think we should have just enough time to be able to go through it. So the small model property says that a sentential formula in first-order standpoint logic is satisfiable if and only if there exists a model of that formula with, at most, length of phi many precisifications. So this means that in your standpoint model, this set pi here, the number of precisifications it contains is bounded by the number of symbols in this formula phi. So the model is small in that regard relative to its set of precisifications. So I'll explain how this theorem is proven. We'll go over some of the cases of the proof. So the right to left direction of this theorem is trivial. If a formula phi has a model with at most length of phi many precisifications, then obviously it is satisfiable. So nothing to really do there. Okay, this just follows from the definitions. The left to right direction is the more interesting direction of this theorem. So let M be a model of phi, which follows from the fact that we're assuming in the left to right direction that phi is satisfiable. The idea of the proof is to try to prune the set of precisifications to obtain a new model, M prime, where the set pi prime is smaller than the length of phi. And the way this works is as follows. It's explained here after construction. We take every subformula which is prefixed with a standpoint box of phi. So sub phi, by the way, stands for the set of subformulae of phi. And we look at every box subformula, and if it's not satisfied in the model M, this means that there is a precisification in M which falsifies psi, right? So we let pi prime be the set of all of these witnesses. So for each box formula, we choose one precisification that falsifies the formula inside of the box. And we just do this for each box subformula. And if it's not the case that there are any box subformulae which falsify phi, then we just select an arbitrary precisification to be put into this set pi prime. Now it's not hard to see that based on the definition of big pi prime, that it's bounded by the number of subformulae in phi, because we choose a precisification for each falsified box, and the number of subformulae of phi is equal to the length of phi. Okay? This is just a fact of logic. The number of subformulae is always equal to the length of a formula. We define in this new model the interpretation of standpoints to be the old interpretation from M, restricted to this new domain of precisifications. And similarly, we also define this new interpretation function lambda, which associates with precisifications first order interpretations, to be the restriction of lambda to the new set of precisifications. And now we can show by a certain induction argument that it is in fact the case that phi holds on this new model M prime. And that's done by establishing by induction on the length of a subformula of phi the following equivalence. We show that for every precisification in pi prime and for every variable assignment v, that this subformula of phi holds relative to m pi and v if and only if it holds relative to m prime pi and v. Okay, so since this is an induction and we have to consider the length of this subformula psi, so in the base case, psi would just be an atomic formula, and in this case, we would have, if we let pi be a precisification in the new model or structure, and v being a variable assignment, if we have that this atomic formula holds relative to m, pi, and v, then by the semantics, this means that the interpretation of all of these terms stands in relation p. Now, since lambda prime is the same thing as lambda restricted to pi prime, these two clauses are equivalent to each other. And by the semantics, it follows that this atomic formula is also true on the new pruned model as well. Okay? Next, let's look at the inductive step, where we consider psi, this formula, to have logical connectives. So in this particular case, we'll assume that psi is a universal formula. So in this case, let us suppose that this universal formula is satisfied on the original model or structure relative to pi and v. Now, due to the semantics, this means that chi holds on m relative to pi and v, where with v, we let x be any arbitrary element of delta. Right? This will hold no matter what. Now, since the new model and the old model share the same domain, it will also be the case that chi holds relative to m prime, pi, and this variable assignment. And by the semantics, this means that for all x, chi will hold as well on this new pruned model. Okay, this will be the last case that I'll consider in the proof. The negation and conjunction cases are argued similarly. They go through similar to the last case. So this is the most interesting case of this argument, which is when the subformula of phi is a standpoint box formula. So we'll show the left to right direction of this if and only if statement first, and then afterwards show the right to left direction. So let us suppose that we have this subformula occurring or being satisfied on m with pi and variable assignment v. Well, then by the semantics, that means that chi holds in all precisifications pi prime in the interpretation of E. Now, since we have that sigma prime in this pruned model is a subset of the original sigma, this implies that chi holds relative to m and all precisifications pi prime occurring in the interpretation of sigma prime of E. And by the induction hypothesis, since chi has a smaller length, we have that chi is satisfied on m prime relative to pi prime and v. Again, for all pi primes in the sigma prime interpretation of E. And by the semantics, this means that this box formula holds relative to the new structure with pi and v. Okay, so that's the left to right direction. The right to left direction is shown by contraposition. So we can assume that this box subformula is not satisfied on m relative to pi and v. If that's the case, then this, of course, means that it does not globally hold on m. And now what happens is, by our construction, we have chosen in our pruned model a precisification that witnesses that this box formula is false. So let that precisification be pi double prime. We have that chi does not hold in the model M on that particular precisification, following from the previous clause. And by the induction hypothesis, since chi has a smaller length, this means that chi does not hold relative to m prime in this precisification, which means that the box formula does not hold as well. So once you've established this if and only if statement by induction, since phi is a subformula of itself, you also have this equivalence holding for the formula phi. And what this is showing, or what is implied by this, is that the satisfiable formula is satisfiable on this new model m prime, which is pruned, which is smaller. So the reason why the small model property is useful is that it allows for us to look at certain logics, like, for example, the logic EL, which is a particular description logic that Hannes will describe in the next lecture. And if we add standpoints to these logics, which are used in knowledge representation, then if we are dealing with or if we add standpoints in a certain way and we focus on the sentential fragment of that logic, it will have this small model property, and one can show mathematically that the complexity on the basis of this does not increase when you've added these standpoints. So this is really the important bit about standpoint logic. We have these knowledge representation languages, or languages which are just used in computer science, and if we want to add standpoints to do standpoint reasoning to them, then we are guaranteed, so long as we are dealing with a sentential fragment of that logic, that the complexity is not going to increase. So this means that from a computational point of view, things have not really changed, but we have these standpoint modalities that are integrated into the language now, which give us more modeling capacity. So in the next lectures, Hannes is going to talk more about these description logics, and we'll also touch on non-monotonic standpoint logic as well. So that covers the lecture for today. Thank you very much for your attention, and have a great day.